All right. I want to talk about this real quick, and then I want to move into 9.4. Okay, so there's some more examples here that we can use if we need them down the road. Come back to them if you get confused or need to brush up on some of this stuff. But the one thing I want to talk about, we might, I'll just give you an image here, and we'll use critical values to do this. But knowing that critical value is directly linked to p-values, let's say that we have a situation where this is our normal curve, and we find a critical value. Let's say our critical value is at like negative 1.3. And that means that anything to the left of negative 1.3 would tell me to reject my null hypothesis. Well, let's say that I get negative 1.32 for a z-test that came from my data. So that's to the left of negative 1.3, right? But let's just say it's right there. Okay? So I do reject my null hypothesis, but it is so close to that negative 1.3. Let's say I find a z-score that was, instead of negative 1.3, let's say it was negative 2.8. That's going to be way down here, right? Would we agree that one of those has a greater degree of, a greater degree of rejection than the other? Like I am strongly going to reject the 2.8 number. But we're on the fence, literally on the fence with that negative 1.32 value, even though it's to the left and tells me to reject. So that's what this statement here says. It says, when conducting hypothesis testing, the researcher must distinguish between statistical significance and practical significance. Okay? Statistical significance says in both those situations, we're going to reject. Okay? But practical significance is the idea that, okay, if I reject here, we do reject, but let's say that we were talking about that question yesterday, I talked about buses stopping. Let's say that the brake manufacturer of those buses realizes, hey, the hypothesized mean is 264. That's the accepted stopping distance going 50 miles per hour, 264 feet. Our sample data says it's not 264 feet, but just to the left of it. So maybe it's 263.5 feet, 6-inch difference. Okay, would that be really something that they want to go out and market? No. If we say that the average stopping distance of all buses is 264 feet, but our brakes, our buses, they stop at 263.5 feet. That's not a big difference, right? That's not practical for them to then market that. All right. Now, if it was, if their bus stops 40 feet shorter than everybody else's buses, is that something they could probably market and use? Yeah, because that's going to be a safety thing that they can utilize. Okay. So that's the difference between statistical significance at 263.5 feet. Yes, you reject that null hypothesis. The mean is not really 264. Okay, even though it's very, very, very close. Okay, we're just on the other side of that threshold. But then practical regards, it doesn't make sense to actually use that. It says when the null hypothesis is rejected at a specific significance level, it can be concluded that the difference is probably not due to chance, and therefore it's statistically significant. So whenever we reject something, we are making the argument that it's not because it happened, that rejection happened not due to a sample, the chance of a sample being different than the population. Does that make sense? We're saying that because it's so far over into the rejection region that the only way that could happen is if the population does not really look like the hypothesized population. Okay? Says, however, the results might be of no practical significance. For example, suppose a new fuel additive increases the miles per gallon a car can get by half a mile for a sample of 1,000 automobiles. The results may be statistically significant at the 5% level, okay? But the results would not be worthwhile to market a product with such an increase. Okay, you want to think ExxonMobil is going to come on and say, hey, our gas gets you a half mile more per gallon. Okay, because it's not a big deal. All right, but if they say our gas gets you, our additive that we put in gets us, 10 gallons or 10 miles to the gallon more, then they can market that. Okay. So that would not be a situation that's practically significant. So the researcher must use common sense when interpreting the results. It says rejecting or not rejecting a hypothesis with a simple yes or no does not express how close to rejecting or not rejecting the hypothesis the data leads to. Okay, this would be a situation where in both those you reject. Okay, but obviously one of them is a lot less significant of a rejection than the other. Okay, a higher degree of maybe rejection. So what was happening? It says we have an established rule of thumb. This is a rule of thumb. It's a guideline. It's not written in stone, but it's a good tool that across statistics gets used frequently. Okay, it says to identify the strength of evidence against the null hypothesis. This is what we do. Okay, if your p-value is less than 0.1%. Less than 0.1%. So we change this to percentage, it's 0.1, right? If it is less than that, we have extremely strong evidence to reject the null hypothesis. Okay? So that would be a situation like this one over here. Okay? We are way far away from that threshold of rejection or non-rejection. Okay? If your p-values are between 0.1% and 1%, we consider it very strong evidence. 0.01 to 0.05, so 1% to 5%, we call it solid evidence. Okay. 5 to 10, we say it's mild evidence. And we've got slight evidence, and then here would essentially be no evidence. Okay. I would argue that, if I put one like this, would be slight evidence, or essentially maybe no evidence, okay, because we're so close. Even though we reject, really no. And the idea here is whatever this alpha was, the level of significance, let's say its level of significance was 5% or 10%. If I change it to 5%, now it's over here, and now I would fail to reject, right? So that would be maybe something that plays in that as well. So we have to be able, when we write a conclusion, we're going to want to come to this table. And to be honest with you guys, and I don't know the questions that we see as we go through the rest of the class, if they're ever going to ask you to determine a strength of evidence, okay? But I think this is added information that is important for us to realize, that we could reject a null hypothesis, but reject it simply because we're just a smidge over from the critical value, and that really doesn't lead you to a true or practical use of that study. I just think that's important for us to realize. Okay, and that's taken into account here with this information. Another reason why a lot of statistical packages will just give the p-value, and they will not make if I write a study about buses stopping distances, I might just say, here's the p-value, and I'm not going to make an argument as the researcher to say, hey, we're going to reject this null hypothesis. I'm just going to leave it up to the reader, okay? And that's why then if you're a reader, you have to be an informed reader. You can't just read something and say, they're going to tell me everything I need to know. I'm going to need to read it, I'm going to comprehend it, and then utilize my statistical knowledge to come to my own conclusions, my own decisions, based on different levels of significance, and then that can help me determine the strength that data provides against the null hypothesis. So I think that's important to think about. Like I said, though, will I need to use this chart directly in math Excel assignments or tests or quizzes? I would say probably not. But I think it is, my thought when we do homework, we do stuff in this class is to make you a well-rounded mathematician, a well-rounded statistician. And there's things out there that even though the tools that we use don't address it, that I think you should know and be aware of, I'm gonna show that. Okay, so I think that's one of those things. Okay, so what do we talk about? How big did our samples have to be in the last 2 or 3 days? Had to be over 30. Okay, they had to be over 30, and we also had to know the population standard deviation, right? Now we've talked in the past that is rare. The only way that we would know a population standard deviation, one, is if we had the entire population, which is impractical, or two, we know from a previous study, and basically we're gonna siphon off that value from previous study and use that as our population standard deviation. That's impractical. But what we've been doing in the last couple days gets the ball rolling. We did the same thing with confidence intervals, but generally it's not going to be the test that you use because you're not going to have access to all the information that is necessary to conduct that test. So when that happens, let's say that we're testing a new therapy on like a new oncology therapy for cancer patients, okay? And let's say that we have a special, let's say like a type of cancer that is very rare, okay? I might not have 30 people I have access to, or more than 30 people I have access to conduct the study with. Does that make sense? Maybe I only got 20 people or 15 people. So then what happens if I can't get to 30? What do I turn to? And the t-distribution allows for that. Okay, so when the population standard deviation is not known, we must use a t-test. So the distribution of the variable should be approximately normal. Okay, we talked previously in chapter 8 that as our degrees of freedom increase, so the more things that you have in your sample, the more the t-distribution morphs into the normal distribution. Okay, yet they are both still symmetric. Okay, and that's the key thing here. Okay, we all the questions, and I think we've mentioned this one time. All the questions that we've done all year, usually they say assume that the population is normal, right? But what if I was doing this on my own? Let's say that I'm looking at doing a study when I get to grad school about I don't know, test scores after some type of treatment that we give students, okay? Maybe I'm looking at ACT scores after students have taken a 3-week ACT prep course, okay? And see, is that prep course impactful, okay, versus not having that prep course. If I'm doing that study from scratch, how do I know that the data or the population is normally distributed, okay? Because I would have to assume that, right? But I'm not sure that assumption is correct. There are things out there, there are tests out there that we can do on our data to give us insight on whether they're normal or not. Okay, it's kind of outside the scope of this course. And if we have time at the end of the year, maybe we'll get into it. A lot of it's called a QQ plot. You take your data, if it falls within some bands on an XY axis, it will allow you to make the assumption of normality then, okay? But that's where a lot of that stuff's coming from, is when they say assume normality, is that the author has previously done like a QQ plot and determined that this situation is normal. The t-test is a statistical test for the mean of a population, and it is used when the population is normally or approximately normally distributed, okay? And sigma, or your population standard deviation, is unknown. Okay, the formula for the t-test, this should look very similar to the z-test, okay? Because what is a good, if I don't have the population standard deviation, if I could not take the entire population, okay, and find a standard deviation, okay, find the spread essentially of that entire population, what is our best approximation for it? The sample standard deviation. Okay, so that's what S is right there. okay, in that formula. And the z-score, or the z-test, that is sigma. We replace it now with S, okay, sample standard deviation. Still divided by square root of n, there at the bottom, so that formula is very similar, okay? The only thing we have to pay attention to that is different is our degrees of freedom, and that's always n minus 1. So if you remember the t distribution, it's a family of curves, and the curve is initially, it's kind of fatter at the tails than what a normal distribution is. But as it's fatter at the tails and it's lower at the peak or the maximum. But as your degrees of freedom increase, the tails thin out and the peak rises, and it becomes very similar to the normal distribution. Okay, and we've seen, I think there was a scenario we talked about where if you have a sample size bigger than 30, then we can make the argument that we're basically utilizing the z distribution. Okay, some textbooks when if you like watch YouTube or anything, like I know some of you get bored and get on YouTube and watch statistical discussions, they'll make arguments that even though textbooks use 30 for the threshold, they'll make arguments that even 100 might not be enough. But regardless, we're going to use 30. It says using a t-distribution table to determine the critical. Do you guys remember doing this? Okay, so we had a t-distribution, so we chose an alpha, and we had to then say, okay, well, our degree of freedom, figure out our degrees of freedom, and then see our alpha and see where those two things intersect. And that right there, that 1.746, then is our critical value. Okay? You can see now that maybe the purpose of having these two rows here, because one's for one tail, okay, so a left or right tail situation, and this here then is a two-tail situation. So you'd have to decide which of those, based on your alternative hypothesis, which column you're trying to, which row you're going to try to intersect here, okay, to find your critical value. I think that it probably makes most sense not even to use this table, because we can use, again, Excel or Desmos, okay? So once you have the critical values determined, then calculate the t-statistics from your data and make a decision about the null hypothesis. Essentially what's going on here, guys, this is the exact same thing we've been doing. There's no procedural things that are any different other than the commands that we're going to use inside Excel or Desmos. Or if you're a table person, you use a different table. Okay? So, and what kind of stinks about this is now we have a second test, right? I'm not going to do this to you right away, but we could start saying, okay, on tests and quizzes, homeworks, maybe I put in maybe 3 questions that are asking you to use a t-test, and the next one, based on the criteria and the problem, says you got to use a z-test. So now we've got to always be processing what conditions need to be met from our data that allows us to decipher now which test to use, now that we have 2. Does that make sense? Eventually we'll have 3 and 4 and 5, and then things start to get fuzzy. Individually by themselves, I don't think you're going to see too much trouble. But when we get to a test or a quiz and there's, 4 or 5 different tests that need to be utilized, you're going to have to look at the scenarios. Okay, I got this condition, this condition, this condition. If I've got those 3 conditions, what test does that target? Okay, and I'll try to my best provide you with that insight. Okay, here it says a medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. Okay, we read that. There's a claim, and there's the phrase, is 16.3, right? That should elicit something for us in our hypotheses. So the random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at alpha equals 5%? Okay, so here's the question. We're sampling weeks, right? Okay, taking the maybe week 1, and we look at the infections that are in week 1, and we look at week 2, infections in week 2. 10 weeks is my sample size, and that's less than 30, correct? All right. So I cannot use the Z distribution here. We have to use the T distribution because your sample size is small. Okay, sample size is small, and the sample standard deviation is known. The population standard deviation is not known. So when we do this, we're going to use a t-test, which is going to be this thing here. And we have to address our hypotheses, so our null hypothesis and our alternative hypothesis. So still talking about averages here, so it's still mu. Okay. Now, it says a medical investigation claims the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. So which hypothesis is this highlighted stuff dealing with? Is it the null hypothesis or the alternative? It's the null, because it's got equality, right? Okay. Now, as we read that, that is actually the claim, right? And a lot that we've done, a lot of the questions that we've done, the alternative hypothesis ends up being the claim. But here, maybe for whatever reason, maybe this hospital is making this claim because maybe it's a marketing thing. Okay, maybe they've got whoever's in charge, HR or whatever, they're coming out and saying, hey, we have 16.3 infections, and that's much better than anybody else in our area. Okay, because now, you know, if I'm a patient, I don't want to go to a cesspool of infectious people to get healthy, right? Okay, so that may be data that people will know. Now it says a random sample of 10 weeks had a mean number of 17.7. Okay, is there enough evidence to reject the investigators' claim? So, are they asking us whether, I'm trying to determine my alternative hypothesis here, does it tell me to look one way or the other in regards to that 16.3? No. So we probably have to use not equal to as our null hypothesis. Okay. Now, several weeks ago, I remember, I think it was Blaze actually asked this question about, like, when it's not equal to, do I know where it's above or below? Our data should actually tell us when we go through this, based on what the z-score that we get back, or sorry, the t-score that we get back, whether we are different than 16.3, and that being above 16.3 or 16.3 and being less than. Does that make sense? Just the size of the t-score that we get. So, what is X bar in this particular question? What does the sample mean? 17.7. Minus mu. Mu, just like when we did the z-test, was established in the null hypothesis. So 16.3. We don't know the population standard deviation, so we insert the sample standard deviation in its place. So S is 1.8 divided by root n, which would be radical 10. Okay. Now we also need to determine our degrees of freedom. Degrees of freedom is n minus 1. So in this case, 10 minus 1 would give me 9, right? And that's going to tell me eventually what curve out of the t-distribution family of curves that we're actually going to utilize. Okay. So we're going to run that information. Okay, so let's grab, I'm going to do it in Excel. Okay, I'm going to hit equals t dot dist. And actually, it's got to be, I'm looking for the inverse. I'm looking for it to give me a critical value back. Okay, so I'm going to type in inverse, or nope, it's t.inv. Okay, so the probability. Okay, so if I'm going to use, we're going to approach this right now using critical values. Okay, so when I do this with critical values, the probability that I'm using is from alpha. Okay, so alpha, just think about this. Alpha was 5%, right? So remember the t distribution still looks something like that. Our mean is still in the middle. That's the null hypothesis. Okay, but now it's a two-tailed test. And because it's still symmetric, that is going to be alpha over 2, and that area is going to be alpha over 2. Does that make sense? So I'm trying to find these t values, these t scores that establish or create the rejection regions. So if alpha is 5%, then because it's a two-tailed test, we need to use alpha in our Excel, or the probability requirement in Excel is 0.025. Okay, so we'll do that. So 0.025, and then ask for the degrees of freedom, which we said was 9. Hit enter, and it gives me negative 2.26. So negative 2.26 and positive 2.26 are the two, call them like demarcation lines. They're the two thresholds that we are going to use to determine if our null hypothesis needs to be rejected or not rejected. And the thing that we're going to now do is take the t statistic. That is the 17.7 divided by, or minus 16.3 divided by 1.8 over root 10. We're going to take this thing here and see where it falls over here in comparison to those two numbers. Okay, if it falls to the left or right of those two numbers, we would reject, because they'd be in the critical regions, right? If it falls between those two numbers, we would fail to reject. So we'll run the calculation on those numbers. So 17.7 minus 16.3. Was it 1.8 divided by square root of 10? Make sure I got all those right. 17.7, 16.3, 1.8, 10. So it gives me 2.459. 2.459. And 2.459, that's the t statistic. That's the test statistic. Okay? Would fall right there, correct? Okay? So what's that tell me? You're going to reject the claim. You're going to reject the null hypothesis. Okay? And that basically means, because the null hypothesis was the claim, is that we have evidence against the claim, or that we have evidence that says we cannot support this claim. Okay? Now, we talked at the beginning about this being not equal to. It's not equal to 16.3. But where did it fall? What region did it fall in? To the right, correct? It fell in that right rejection region. So does that tell me that we have more infections than the 16.3 that's being the claim? Does that make sense? Okay. If it fell to the left, then we would say we'd have less than the 16.3. Okay. But here, and basically what we could do, if I'm like a third party trying to investigate this claim, maybe we make the argument that, hey, this hospital is being maybe not forthcoming, or so forthcoming with their data as they should. Okay. Maybe they're suppressing things. Does that make sense? And then you don't always do those types. You don't always think that somebody's doing something nefarious with their data. Maybe it's just an oversight, or maybe it's not intentional. Does that make sense? But maybe this could provide a motivation to maybe start investigating a little bit more for what's going on. Does that make sense? Okay, maybe it starts to lead to, okay, if that's the case, we have more infections than what we think we do. Maybe we start now establishing more policies, more protocols, and those types of things. Guidelines for dealing with patients, guidelines for wearing masks, wearing gloves, that kind of thing. Okay, so those are always things that are byproducts then of having the data and having the information in front of us like this. So that's a t-test. My plan is to continue spending time on that in the next several days. The key thing, though, in deciding z-test or t-test, how big is your sample, and is the population standard deviation known or not known? And that will allow you to make the decision. Okay. Excuse me? The z-test was what we were doing yesterday, day before, yeah.